Hi, GSA. Thank you for coming to my talk. I'm excited to talk to you today about fault locking processes and subduction zones. After an earthquake, it takes some amount of time for faults to lock up. This time scale might be revealing about the process that causes faults to lock. This matters because the time scale affects recurrence interval and the size of slip deficits that can develop over time. Changes in plate boundary behavior, like changes in strength with time and space, need to be explained by geologic processes. And we do have a record of these processes. We have the rock record of earthquakes and associated activities within fault zones in exhumed faults from all over the world. Timescales of locking are easily observed in several different types of data sets. Kallenwang's summary figure here shows how the change in the direction of the forearc reveals the degree of locking on the megathrust. The left panel shows Sumatra in 2005, and the forearc here was still moving westward, trenchward, the same direction that it slipped during the Great Earthquake of Boxing Day 2004. Movement parallel to the lower plate indicates locked and loaded plate boundary, which will rupture soon, as shown in Cascadia, which is here in the right panel. In the center panel, you can see Chile prior to the 2010 Male earthquake. And at this point, when these data were collected, the movement in the southern part of the margin is very small, almost zero, because the trenchward movement following 1960 has ceased and locking has occurred on the megathrust, and the upper plate is about to get pushed landward in a style more like Cascadia in the future. In the northern part of the margin here, you can see the margin was already locked and loading for the next earthquake, which finally occurred in 2010. So in all these cases, we can see that it's a decadal to maybe centuries time scale in between the time of a great earthquake and the time where the fault is very clearly locked. Stein and Liu showed the aftershock distributions for earthquakes in a variety of tectonic settings. Plate boundary earthquake aftershocks dissipate in decades after an event, as you can see in these larger earthquakes on the right here. And areas with lower tectonic strain rates actually take longer, like the ones in the center and the left side of the plot. Tiansen and others showed that the timescale of locking predicted by models which simulate the viscoelastic response of the mantle to earthquakes on subduction plate boundaries. His result shows that the bulk response of the rock in the plates to an earthquake takes a few decades to relax. But plate boundary zones are not just passive blobs sitting there in the earth waiting for an earthquake. In the background of the earthquake cycle, there are a lot of slow changes that go on in and around the plate boundary. In subduction zones, the footwall rocks experience a change in pressure and temperature conditions that leads to progressive metamorphism, and the hanging wall of subduction zones is a dynamic Coulomb wedge that is constantly deforming. These down-dip changes, along with an increasing load with depth, contribute to broad-scale strength trends. The earthquake cycle, which involves a sudden stress drop and decades of recovery we have just discussed, is superimposed on this trend. So we can expect when looking at exhumed faults from the seismogenic zone that we're seeing the cumulative effect of long-term strength evolution and the short-term rupture and recovery on the plate boundary rocks. So, what do we know about geologic conditions that can control the strength of rocks and therefore the strength of faults? If we know what these are, then we can explain the process of fault locking by changes in one or more of these domains. Lithification is the increase in strength and cohesion of a sediment through compaction and cementation. Since fault rocks are often granular and similar in texture to sediments, we can apply this process similarly to granular fault rocks and other kinds of secondary porosity. It refers to the filling and collapsing of pores. Geometry describes the straightness or roughness of a fault surface or the network of fault surfaces. Mineralogy describes the minerals that are present on or near a fault surface, which controls rock behavior, such as determining the deformation mechanisms that would act at particular conditions. Fabric is the degree of alignment and connectivity of mineral grains in a rock, which is important for determining which of the minerals will actually control the bulk rock. Here I'll stop for a small aside. These four phenomena I've just described would be treated very differently if you think of a fault as a single frictional interface, as is approximately true for earthquake slip, or if you are thinking of the whole volume of rock that deforms during different stages of the earthquake cycle. Field observations very clearly show that for faults of all sizes and tectonic settings, there are usually large volumes of acutely deformed rock around the principal slip zone. The locking of faults requires that the whole fault zone needs to be strong or strengthened, So for the most part, it doesn't make sense to describe fault locking by the frictional evolution of a 2D interface. In subduction zones, there's a particularly common fault rock called Scaly Fabric. It's a poorly understood anastomosing network of shear surfaces that forms in clay-rich rocks by some combination of distributed slip, compaction, dilation, and solution creep. Matt Tarling sheared lentils in a small sandbox-style setup to see how they rearrange during shearing, and we found that the slip in this kind of geometry continually reorganizes. So there's lots more to learn about the strength and behavior of scaly fabrics. This matters when thinking about locking, because if deforming is not locking, then we need to clarify what conditions are needed to stop deformation from happening in order to see a locked fault when the far-field stressing is still ongoing in the background. In this context, thinking of a fault only as a 2D slip surface leaves only frictional sliding to consider. But in the real world, deformation in thick faults and fault zones plays a huge role in fault motion, so also must play a huge role in locking. So now I'm going to go through these 4 domains and think about how they work and how they can evolve with time. Lithification, which I'm going to define as compaction and cementation, can work on long time scales. For example, it works during subduction of trench sediments and in monotonically increasing lithification state with depth. Immature, poorly sorted sandstones, like the example on the left, which was subducted to about 3 kilometers, transform over time to low porosity, strongly foliated samites like the one at right, which has been subducted to about 30 kilometers. And the principal mechanism for doing this is through solution, removal of material to close pores and contacts. Cements can also precipitate quickly to fill cracks and heal fracture damage, like this damage zone example from an out-of-sequence thrust. Rates of solution creep can be calculated easily from a few basic assumptions. Solution creep can be really efficient in small grain-size fault rocks in the seismogenic zone. In fact, becomes efficient at about 150 degrees C, which correlates very well to the upper limit of the lock zone in most subduction plate boundaries. Second, geometry. Fault surfaces which are very bumpy are interlocked, making sliding more difficult. The examination of layers of fault gouge in faults show that the bumps in faults are cut off by subsequent slip that breaks through, so the fault can become smoother with slip. But those interseismic processes of healing that we just saw in the previous slides can modify the smooth faults and make them uneven again. Here's an example from a subduction zone, a thin, sharp, and wavy thrust fault, part of an imbricate stack that repeats 17 times in this particular terrain within the Franciscan complex. Based on the age of the involved sediments and the convergence plate rate from global plate models, we estimate that if each imbricate develops successively, then the timescale for cutting a new thrust is about 10 to 100,000 years. So that's one estimate of the timescale of geometric reorganization that you could use to understand a fault system. Geometric changes can occur with every increment of slip, as shown in the experimental examples, as well as over the lifetime of the fault system, as shown in the block diagram from the Franciscan complex, and this recent seismic section off Costa Rica, where an abandoned megathrust segment can be imaged. This one was taken from Kirkpatrick and others 2020. The black arrow indicates the currently active plate boundary fault, and the white arrow indicates an abandoned segment. Subduction zones have an interesting and unique feature that the mineralogy of the rocks in the footwall evolves in a predictable way as pressure and temperature increase with depth, or rather, as the rocks progress deeper through pressure-temperature space. The plate boundary might form in subducting sediments, which can be quite diverse, bringing variable amounts of water. Basalts of the lower plate also become incorporated into the plate boundary zone, contributing to heterogeneity. The processes of metamorphism and metasomatism, which are advanced during the subduction of these rocks, increase the heterogeneity. Here's 3 examples of metabasalts that have very different mineralogy and fabrics, some of which is driven by the infiltration of fluids into the rock. In general, the metamorphic and metasomatic processes are unlikely to have big effects on short timescales comparable to the earthquake cycle, even if the fluid flux is modulated by permeability changes during and between earthquakes. But broadly, prograde metamorphism can explain a lot of the broad trends in fault strength, especially when considered alongside fabric evolution. The arrangement of minerals, specifically whether the weakest phases in a rock are linked, like in this example of shear fabrics and calcite talc from the Scaly fault. Linking up the talc grains makes the whole rock as weak as talc, even though there are lots of other minerals present. This works on a lot of scales. For example, these are chlorite-rich metabasaltic boudins in the Mugi melange, and they're much more prone to slip than the surrounding argillite, which is siliceous. So these wispy tails smearing along the faults could focus slip through an otherwise strong shear zone. Experiments have shown that fabrics can change very quickly during slip and are very sensitive to slip rate and pore pressure conditions. They can also form by a combination of granular flow and solution creep, like in these halite muscovite gouges that were made by Niemeyer and Spires. So these four domains are clearly intertwined and interdependent, but we can broadly associate timescales to the processes that control them. Lithification can be associated with both fast healing after an earthquake and also with the long-term trends over many millennia, and therefore with the down-dip changes in rock properties and strength. The geometry of fault systems is dynamic. It can change quickly and slowly and probably affects the strength during any slip event or earthquake. Mineralogical changes are mostly constrained to long-term evolution, and structural fabrics, the volume equivalent of geometry basically, can change fast or slowly and can be modified with every slip event. To briefly define some of the interdependencies at play here, let's look at some of the feedbacks that contribute to fault locking on short time scales. That is, the processes that could operate in a post-seismic period leading up to locking for subsequent earthquakes. Lithification is advanced by compaction and cementation, processes that facilitate pore sealing. This process is very anisotropic as it is advanced by solution creep operating under differential stress. So the outcome is fabric development, which affects the anisotropy of permeability and therefore modulates further solution creep and lithification. That fabric anisotropy controls slip localization and thereby controls the parts of the fault that slip, aka the fault geometry. The geometry of pre-existing faults also controls slip distribution, so feeds back on the development of fabrics. The bumps and steps in a fault control the stress concentration, which drives local lithification processes. Meanwhile, it's the lithification which cements formerly weak layers and causes slip redistribution, changing the fault geometry. When we extend the timescale out to look at the long-term evolution of fault rocks during subduction, we can then also include the evolution of the mineralogy that's driven by metamorphism and metasomatism of the subducting plate and of some upper plate rocks. The mineralogy determines the viscosity of creep at the deeper depths and the coefficients of friction and the weakening mechanisms that act in the shallower parts of the fault. Mineral mixtures control fabric evolution, in particular in phyllosilicate rocks. Changing mineralogy also creates and destroys strength contrasts, which can have a huge effect on the geometry of the deforming zone. For example, as parts of the fault zone rock undergo blue schist to eclogite metamorphism, the strength heterogeneity is greatly enhanced. So to summarize, the fault locking has to be controlled by changes in the factors that determine fault strength in plate boundary zones. The evolution of strength is fundamentally controlled by the deformation processes and the fluid rock interaction that takes place in and around the plate boundary, which we must think of as a broad zone that encompasses any part of the rock which could fail in slip or creep. This is what the big deformed zones in exhumed subduction complexes are telling us. Thank you very much, and thank you to Eric, Danny, and Kevin for the invitation to talk to you today.